So I promised you in the last video that I would show you that the sequence of harmonic sums diverges, and that's what this video is about. Alright, so we're going to look at bounded and unbounded sequences again, look at the definitions, get our heads around that one so we know what we're talking about. We're going to define the sequence of harmonic sums in case you've forgotten what they are, and then we're going to prove the sequence of harmonic sums diverges. Alright, so we have two equivalent definitions of what a bounded sequence is. So the first one is that there's a lower bound little m that's less than or equal to all the terms, and an upper bound big M that's bigger than or equal to all the terms. And then there's another where we look at the absolute value of the terms, and that is bounded above by some real number m. Also recall that every convergent sequence is bounded, but the converse isn't true, right? If you have a bounded sequence, it's not necessarily convergent. A great counterexample is -1 to the n. That is certainly bounded. It's between all the terms are between -1 and 1, or if you like the second definition, the absolute value is always less than or equal to 1. But the sequence is not convergent because it never gets close to a particular number. It just flips back and forth between -1 and 1. But we can use the connection between sequences being convergent and sequences being bounded in other ways, right? So for instance, if we happen to have a convergent sequence, we can conclude that the sequence is bounded. We can take the contrapositive of that, which says that if we happen to have a sequence that is unbounded, we can conclude that it is divergent. All right, so that's exactly what we're going to do with the sequence of harmonic sums. So just to remind you, the sequence of harmonic sums, we have 1 plus 1/2 plus 1/3 plus 1/4, etc., all the way out to 1 over n. And just to put this in a little bit of context for you, back in Calculus 2, if you're thinking about it in those terms, this is the sequence of partial sums of the harmonic series 1 over k. Right? Sum of 1 over k. And you may recall, maybe you were just told, or maybe you actually went through an explanation of why it's true, that this series diverges. That's essentially what we're doing here. So if you've seen this before, or it looks familiar, that's probably why. And the way we're going to prove this is we're going to prove that the sequence is unbounded. So let's go ahead and try to look at some of the terms to see how big they're getting, to see if we can find out maybe some upper or lower bounds to help us figure out that they are getting divergent. So our A1 is just equal to 1. I mean, it's just 1. Not much we can do with that one. Our A2 is 1 plus 1/2. I guess we could simplify that to 3/2, but I'm going to leave it there just to see if we can use that to find some patterns. I'm going to skip A3 and go right to A4. We have 1 plus 1/2 plus 1/3 plus 1/4. And notice that if we replace that 1/3 with 1/4, we'll actually make that sum smaller, but we'll make it a little easier to simplify. So if we do that, we get a smaller sum, 1 plus 1/2 plus 1/4 plus 1/4. And notice that when we add those two 1/4, we get another 1/2. So we end up with 1 plus 1/2 plus 1/2, which I'm going to write as 1 plus 2 1/2 because we're adding 2 1/2 to the 1, right? Maybe there's a pattern there. If you notice A2, we had 1 plus 1 1/2. And now we have 1 plus 2 1/2. And where do you think we're going to get 1 plus 3 1/2? Well, yeah, so that's what we have. A4 is greater than or equal to that. The next one's going to be A8, right? So A8 is 1 plus 1/2 plus 1/3, all the way up to 1/8. If we make the 1/3 into a 1/4, that'll make it smaller. If we take the 1/5, 1/6, 1/7, turn those into 1/8, that'll also make it even more small. And so we end up with 1/4 plus 1/4, right, when we turn the 1/3 into a 1/4. And then when we turn the other 4 into 1/8, we get 4 of those. So notice that we have the 1/2 from the 1 plus 1/2. Those two 1/4 make another 1/2. That's our second 1/2. And now we have 4 1/8. That gives us 4/8, which is yet another 1/2. So now we have 1 plus 3 times 1/2. And you might wonder, well, where is the next place we might find this pattern? I think you figured it out. 16, right? So in general, what it looks like is that a sub 2 to the n is at least 1 plus n times 1/2, which is the same as saying it's at least 1 plus n over 2. And that's the little lemma that we're going to prove. And it might not shock you, but we're going to prove it by induction. So we already proved the n equals 0 case. A sub 1 is greater than or equal to 1. Now for the induction step, we're going to assume that a sub 2 to the n is greater than or equal to 1 plus n over 2. And we're going to show that a sub 2 to the n plus 1 is greater than or equal to 1 plus n plus 1 over 2. So first note, if we want to actually find a 2 to the n plus 1, there are a lot of terms in there, so we're going to take a couple breaks. We're going to start with 1 plus 1/2. And the first break that we're going to take is when we get to 1 over 2 to the n, which is somewhere in the middle of our sum. And the reason we're going to stop there is the terms up until then give us a sub 2 to the n, which is going to help us with that induction hypothesis. And then after that is 1 over 2 to the n plus 1, right? And then we keep on going until we get to 1 over 2 to the n plus 1. So as I noted, when we add all the way up to 1 over 2 to the n, that gives us a sub 2 to the n. So if we, and then also that last one, that 2 to the n plus 1, that is the same as 2 times 2 to the n. And 2 times 2 to the n is exactly the same as 2 to the n plus 2 to the n. We're going to write it that way because it'll help us figure out some stuff, right? So if we put in that information, we get a sub 2 to the n plus 1 equals a sub 2 to the n plus 1 over 2 to the n plus 1, 1 plus 1 over 2 to the n plus 2, all the way to 1 over 2 to the n plus 2 to the n. And writing that parenthesized sum that way helps you see that there are 2 to the n terms, right? We start with plus 1, we end with plus 2 to the n, so there are 2 to the n terms there. Also notice that the biggest of those denominators is the last one. The smallest term is the last one. So all the other terms before that are going to be bigger than that. So we're going to do exactly what we did before. Replace all the terms with the all the terms in parentheses with that last term so that they're all the same. All right, so as I mentioned before, there are 2 to the n terms past a sub 2 to the n. Each one is at least 1 over 2 to the n plus 1. That's the last term. And so here's what we end up with. Our a sub 2 to the n plus 1 equals a sub 2 to the n plus all those terms in parentheses that we had before. We're going to replace all the ones in parentheses with 1 over 2 to the n plus 1. So we got a sub 2 to the n plus a bunch of 1 over 2 to the n plus 1s. How many? Exactly 2 to the n of them, right? There were 2 to the n terms. And now we can do a lot of cancellation. We have n plus 1 factors of 2 in the denominator. We have n factors in the numerator. When we cancel them all out, that gives us a sub 2 to the n plus 1/2. Now we can use our induction hypothesis, which implies that a sub 2 to the n is at least 1 plus n over 2. So that tells us that a sub 2 to the n is, remember, greater than or equal to a sub 2 to the n plus 1/2, which is greater than or equal to 1 plus n over 2 plus 1/2. And if we combine those last two terms, that gives us 1 plus n plus 1 over 2, which is exactly what we were trying to prove. That completes the proof. So we now have a sub 2 to the n is at least 1 plus n over 2. Notice that that 1 plus n over 2, that is an unbounded sequence, unbounded function, unbounded sequence, same thing, right? Since a sub 2 to the n is at least as large as our unbounded function, as our unbounded sequence, that means that a sub n is an unbounded sequence itself, which means that it diverges. And that's our theorem. All right, so now there's no activities to go along with this video, but the next video is on Cauchy sequence and convergence. I would encourage you to actually look at some of the in-class activities that go along with that video. right now. I'm going to actually put those activities right below this video as well, so you can look at them. If you don't want to go right into the video, that's fine, but just realize that doing the activities might make the video make a little bit more sense.